G'day, my name is Bruce Robertson and this is Pirate Philosophy. In this series of videos I will be describing an original philosophy, one that you won't find anywhere else, but it is one that is logical, rigorous and dynamic. Welcome. So far in this series of videos and our journey into philosophy and the evolution of mind, we have covered a variety of topics. The journey started in PP8 with As Deep as You Can Go in philosophy, where we looked at the foundation of the separation of mind and matter. We then looked at how a logical processor can begin to create a model of the world, and realized that the only logical process which could achieve this was one of assembling sense data and then seeking to identify patterns within it. Subsequently, the identified patterns can be used as data in the pattern identifying process in a sort of recursive way to create patterns of patterns. And continuing this recursive pattern identifying process, a whole pyramid of patterns can be created, which then constitutes a model of the world. If you haven't watched PP8, PP9 and PP10, you might find it useful to do so before continuing this video. We also looked at reality and purpose, the theory of consciousness, the logic of decision making, and in the previous video we looked at mathematics and how it fits in with our model of the world. Today I want to look at science, i.e. the philosophy of science. So the title of this video is The Real Philosophy of Science and Its Implications for Quantum Weirdness. And some of the questions I want to answer, or at least to look at, is what is the process of science? Why has it been so successful? And how can a philosophy of science contribute to science itself? And science is really just a continuation of the logical processes that we use to build a pyramid of patterns and a model of the world. But whereas much of the logical process for forming a normative model of the world, i.e. from base sense data, is subconscious. We're not aware of it. It is hidden to our conscious minds. Science, on the other hand, is entirely explicit. It takes place in the higher realms of the pyramid of patterns, i.e. in the conscious mind. And there is another difference as well, in that instead of receiving data on a fairly passive way and then making patterns of sense of it, science actively seeks out new data, doing experiments, developing specialized detectors that can reach beyond the realm of our simple senses. And so, for example, the non-scientific normative view of the world would look for simple patterns of the form that the Earth is flat, the sun goes around the Earth, and that with regard to pushing a cart, constant force produces constant speed. But science has sought out data beyond the normative domain and has shown that there are better patterns that can be found that describe the same data and other data as well, such as the Earth is a sphere. The Earth goes around the sun, and that when friction and air resistance are taken into account, the constant force produces a constant acceleration. In PP9, Patterns, Time and Space, I introduced an algorithm to show how information can be gleaned from sense data with no prior assumptions as to the nature of the sense data. The instructions of the algorithm read: 1. Assemble the data. 2. Input a template. 3. Test the template, does it fit? 4. If it fits, continue, otherwise return to step 2. Otherwise, store the template together with a label for the data. And I went over that in PP9. In this video, I want to discuss this algorithm in somewhat more detail and to how it can apply to science. So for that, I've put together a more detailed algorithm, which is this. And from a mathematical perspective, the aim of the algorithm is to compress the data. In order to do this, one needs to find a pattern that can be described in a more compact form than the raw data, and which also fits the data to a required degree of accuracy. And perhaps the algorithm I'm describing applies most to physics, perhaps more so than other sciences, but it certainly can be fitted to any science. So I'd now like to go over the algorithm line by line. Line 1. Assemble the data and give it a label. The assembled data would need to have something in common with each of the other bits of data, to the extent that it may be possible to find a pattern that describes all the data. And to this extent, the range of the data defines the domain of the pattern. We'll come back to this point later. I.e., the patterns have a limited domain. They fit the data, but not necessarily can be extrapolated. You can extrapolate a pattern, obviously, but whether it fits in the domain beyond the domain of the original data is something that has to be determined or checked. Line 2, select a template. This is perhaps the most interesting part of the algorithm, for it requires what we might call imagination to concoct a possible template for the pattern. A template is a possible pattern. It is what will be tested to see if it fits the data. It can be anything at all. There is no limit to what could act as a template. It could be entirely random, or it could be a section of the data, or it could be a template from an entirely different domain, or it could be a combination of two or more other templates. Examples of templates in physics or mathematical terms might be y equals x, y equals 3x, y equals x squared plus 2, etc. Line 3. Apply and expand the template to the data. To show how this works, I have put together some data which is displayed in a two-dimensional form. Here the data is little more than a scatter diagram, but it will suffice for this example. Then suppose that the first template is something like y equals x, which can be represented by a diagonal line. So this diagram shows how the proposed pattern would look within the domain of the data. Line 4, measure the difference between the applied pattern and the original data. So what you can do here is drop lines from the data points to the pattern, as in the diagram, and we can get an indication of the differences between the data and the pattern. And this is how it would look in the diagram. Line 5, sum the differences. When you've got that, you can then add all the lengths of the differences to get an overall indication of how accurate the pattern is. And this could possibly be refined by using the squares of the differences or using some other analytic method of assessing the accuracy of the pattern. But for this, we will just add up the lengths of the differences. Line 6, store the template and the sum of the differences. So you need to store this information because we will be using it later. Line 7, are there any other templates to test? So here you can put in other templates like y equals 2x or y equals x squared or whatever you like, and go through that process again of applying the pattern or the template to the data, looking at the differences, summing up the differences, and then storing the sum of the differences alongside the details of the pattern. And if there are no more templates to test, then continue to line 8. Line 8, of all the templates tested, select the one with the least sum of differences. So here we're selecting the template or pattern that best fits the data. So in order to do that, you look through all the stored sums of differences to find the least sum. Then you take this template associated with the least differences, and this is your best pattern. And you then store this pattern alongside the label given to the data in lane 1. So then you've got a label for the original data, and you've got a pattern, and you associate the two, and you then store that. This algorithm, or at least a variation of it, lies at the heart of the scientific process. And I've shown a fairly generalized form of the algorithm, the bare bones, if you like, of the scientific process. It can be modified so that it can be applied to any branch of science. Also, I have shown this algorithm using only the criteria of accuracy to determine which pattern to select. But there is also the criteria of the simplicity of the pattern, which could be used if no one pattern stands out clearly, using the criteria of accuracy. And sometimes a particular pattern will fit the data exceptionally well, and no other pattern fits the data at all well. In this case, the pattern can be used with confidence. For example, Newton's laws of motions are highly accurate in determining the motions of matter. Other times, no particular pattern will stand out above the others, as for example in trying to determine the connections and family tree of early hominids. A pattern identifying process such as this is the only way that knowledge of the world beyond our senses can be ascertained. As previously mentioned, it is a continuation of the pattern identification process that we personally use to create our pyramids of pattern and a model of the world. And similarly to our own personal pyramid of patterns, science too has a pyramid of patterns, where one pattern is built upon the foundation of others. So, for example, the theory or patterns relating to quarks are built upon many different patterns that have been established by conducting many different experiments that build up patterns relating to quantum particles, atoms, molecules, matter, and perhaps so far as our fundamental notions of time and space. So there's a pyramid, a hierarchy, if you like, of patterns built upon patterns, etc. And in this way, our personal, individual models of the world can be extended to new domains and new knowledge. And that's what science does. And some may be concerned by the lack of certainty in the pattern identification process. All one arrives at is a best pattern and not a perfect one, or at least not one that can be shown to be perfect. But this is not a problem, as all one needs for one's model of the world, whether personal or scientific, is sufficient accuracy to be able to interact effectively with the world. And science has shown this and done this with its technology spin-off, which has created things like cell phones, computers, other things that would be entirely impossible without an accurate model of the scientific world. But of course, this inherent uncertainty can create paradigm shifts within science, as mooted by Thomas Kuhn, where a pattern within the pyramid of patterns, perhaps fairly low down, gets replaced by a better pattern. And this can cause a ripple effect on up to all the other patterns that relied upon it, a paradigm shift. And what one ends up with is an accurate model of the world, and yet one for which there may be, or always be, room for improvement. What this means is that one has an accurate description of the world. And while the laws of physics constitute an accurate description of how matter moves and interacts, one cannot claim, at least not within the philosophical domain, that matter obeys the laws of physics. And perhaps I should also mention the role of mathematics in physics. Mathematics is an extremely useful tool for finding possible templates for the pattern identifying process. However, as described in my previous video, PP15, the 4 components of mathematics, mathematics is in essence an entirely abstract system. mathematics is an abstract system for the manipulation of symbols according to specified rules. And it requires a mapping from those symbols to elements within a pyramid of patterns for mathematics to have any connection to a non-abstract world. So it requires a mapping between the symbols and a measurement or a data or a pattern or whatever it is. It's a mapping between the two, and only in that way can mathematics relate to the world beyond our senses. Science is a process carried out by many different people and groups of people, and some may come up with different patterns or theories which they claim to be good patterns or good theories, but which may be at odds with other people's theories. So the question is then, what test can one apply to a theory to determine its efficiency? And perhaps the best test is, can the theory or pattern recreate the data to a sufficient degree of accuracy? This test would be particularly effective with hand-waving pseudoscience theories, which in general are entirely ineffectual at recreating data. So that pretty much sums up the pattern paradigm approach to the philosophy of science. At the core of it is the algorithm I have described. And of course, once you have those patterns, you can extrapolate them and use them for creating technology and all those sorts of things. And why an algorithm, you might ask? An algorithm because it shows explicitly the logical steps by which the process works. And while the algorithm may be crude and would certainly need some tweaking to fit each of the various scientific disciplines, it does demonstrate the essentials of the scientific method. And that scientific method is used for gaining information about the world beyond our senses. And the reason that science has been so successful, at least compared to standard Western philosophy, is that it stays close to the facts of the world and does not venture into the domain of fantasy. Also, its processes are a natural continuation of the way that we learn about the normative world of everyday life. Standard Western philosophy has attempted and failed to force-fit the processes of science into its fantasy world of words and stubborn certainty. And all it has achieved, if you want to call it that, is to distort the essential nature of science. And finally, I'd like to look at what are the implications of this philosophy of science for science itself. I would like to go over a few suggestions or possibilities that might apply to the wonderful world of quantum weirdness. Patterns that are identified only have direct relevance to the domain of the data from which it was created or identified. While it may be extrapolated beyond this domain, it may not necessarily be accurate in the new domain. So, normative concepts of time and space and matter may not be effectively extrapolated into the domain of the very small or the very large, or the domain of large masses and high velocities, as has been shown with special and general relativity and quantum mechanics and quantum weirdness. When one is trying to make sense of the unknown, as with quantum weirdness, no possible pattern or template should be rejected out of hand simply because it is in contradiction with a pattern in a different domain. So it is not necessary for theories of physics to meet with normative perceptions of the world. They only need to fit the data and hopefully be able to reproduce the data. So there is no requirement to meet with dubious normative perceptions of existence, time, space, causality, and so on. The pattern identifying process enables us both personally and in science to create a model of the world. This model resides in our brains or minds, and it is quite distinct from the world beyond our senses, whose existence we can only infer or hypothesize. In fact, the existence of the world beyond our senses is a best pattern to fit the relevant data. It is perhaps naive, though understandable and acceptable for non-philosophers, to conflate the two and assume that our model of the world and the world beyond our senses are equivalent and identical. So all we actually know about the world is our model of the world, and that can only be created through a process of pattern identification. In most circumstances, it makes no difference whether you think of that you have a model of the world or you know exactly what is the world beyond our senses. But in the limits of science, this may become important. And so this philosophical approach may be useful for resolving the famous Schrodinger's cat thought experiment paradox. For while it may be the case that the best pattern to fit the data for a quantum particle is that it is in a superposition of states, i.e. that there are two states existing simultaneously until further data is received or a measurement is made, this is only within the model of the world that we have. So when it is claimed that Schrodinger's cat is in a superposition of states, of being both alive and dead simultaneously, it is only our knowledge of the situation that is in a superposition of states. And there is hence no requirement for the cat itself to be in a superposition of states. One of the tests for a good pattern is that it can reproduce the data. Another requirement is that the pattern constitutes a compression of the original data, i.e. the pattern needs to be simpler than the data. And the more simpler it is, the better for a given accuracy. One of the proposed explanations for quantum weirdness, and in particular the unpredictability of the collapse of the wave function into a single data point, is what is called many worlds. This asserts that the wave does not collapse at all, but that the world splits into many different worlds with a different outcome in each world. However, as a scientific theory, this many worlds theory fails on both the criteria mentioned earlier. Firstly, it is incapable of reproducing the data of the world we actually live in and experience. It cannot reproduce the data of where the wave actually collapses. And two, neither is it a compression of the data. The many worlds hypothesis is highly complex, with many unanswered questions such as, what happens in the other worlds? Where are they? How many other worlds are there? What are the exact criteria for a world to divide into many worlds? Its complexity far exceeds that of the original data. In the light of this, it would seem that the many worlds theory or hypothesis is not a good pattern or theory. Well, that is all I have for you today. If you have any interesting comments or questions about today's video, please leave them in the comments section below. And if you would like to continue this journey with me, then please subscribe to my channel, give it a thumbs up, and ring the bell. Thank you.